Ah, so now switch off. Can you hear? Yes. Can you hear? Around 10 members. Is this slight change? Hmm? That's was one. Okay. Now it's moving, right? Okay. So good afternoon. Uh, Welcome to the FDP program at the School of Computer Science Engineering and Information Systems is organizing, and we are at the second day afternoon session. So, so far we have discussed in the sessions various aspects of quantum computing, starting from physical aspects, then mathematical aspects, and Professor Ganeshan sir has discussed in the morning about the quantum gates. I will continue the discussion. As we have mentioned, this entire FDP structured across our syllabus that what we have for BTech IT students. So in that regard, we are covering the concepts that are there. So I will extend from what so far we have discussed, and at times or in some places you will come across those concepts that what already was discussed, but you would understand how you can see the same concept in a different perspective, and also that will give you a reorientation of what was discussed. So proceeding further, all of us have come to a point now, what is quantum computing? Morning someone was asking some questions about, sir, these the vector spaces, the matrix algebra, then these complex numbers, they're already there, and then you are saying this quantum computer, and then what is the gain actually? See, if you, the fundamental question for that is a really interesting question, because underlying mathematical principles, these are all there in the literature. Now, what is that the gain we are getting? The gain we are getting, to answer that, you will see that this presentation would answer that as well as other points. So, just to get a glimpse, we all know that we have seen coins. Coins has two faces, head and tail, and when you keep the coin on a flat surface, it faces either head or tail, meaning we say that coin has two states or two phases, which is head or which is a tail. Now imagine, that means when I have a single coin, I have either head or a tail. Imagine if I have two coins, then so from a single coin, two phases or two states. Now I am having two coins. I am getting four states. Meaning, what are those four states? One coin could be head, another coin also head condition or head state. One coin could be in the head, another is in the tail condition, or tail head or tail tail. So meaning, when I have a single coin, I have two states, head or tail. So now when I scale it up with the two coins, I have four states. So meaning two coins, two states. So it is four possible states for two coins. Now imagine I'm adding one more coin, which is the third coin. Now what happens? We get 2 power 3, which is 8 possible states, right? So meaning you are having two states for every coin, and there are three coins such you have. So 2 power 3, totally 8 possible states we are getting, right? Starting from all heads to all tails. So meaning we have started with a single coin with the two states, two coins, four states, three coins, 8 states, and then we can continue. So the more we continue, so take an example, if I have n coins, how many possible states I would get? 2 power n possible states I would get, right? Now why we are discussing this? So with n coins, I would certainly get 2 power n possible states. Now why we are discussing this? So let us keep coins aside for a moment. Let us take another structure. What is the structure I am taking? I am taking a structure which is having six-sided. Earlier structure, what is that? Two-sided. Now it is six-sided. So when I take a single structure which is called a dice, it is having six-sided. It has six sides, right? So what are all the possible sides, states? So you can see based on the number of dots that it is having, 1 to 6. So meaning I have a coin with two states. Now I have a dice with six states, right? Imagine now I am having two dice. If I am having two dice, then what happens? So these are all the possible states wherein which 1 1 to 6 6, right? So first dice 1, second dice 1, like this. I have all possible states when I have two coins or two dice, wherein which each dice has six states, right? So which is like the same, which is represented in the form of a matrix kind of a structure. So since each dice has six possible states, so 6 square, that is 36 possible states for two dice. When I have two dice, I have 36 possible. When I have coin, it is 2 square, which is 4. Now here it is, since it is 6 sides for each dice and there are two dice, so 6 square, I have got 36 possible states. Now imagine I have n dice, so I will get 6 power n, right? So if it is coin, I am having 2 power n. If it is dice, it is 6 power n. Now again, why we are discussing this? Now imagine I wanted to quantify how much of the information that the coin would carry, dice would carry. If this is the question I have, then consider, imagine, let us take, I have a colors of rainbow, right? So we have WebGR, these 7 colors, and these 7 colors RGB. Morning sir was mentioning about various RGB values. So imagine that we are encoding these RGB values by the possible combinations of either coin or through dice. So imagine I have all the colors of WebGR: red, green, orange, yellow, blue, indigo, all 7. If I take coins, I need 3 coins. I need 3 coins at least to represent red, to represent orange, to represent yellow. All these colors I need minimum of 3 coins. Whereas if I have dice, I can represent with 2 dice, because totally 7 colors are there. If it is a coin, I am getting, if 1 coin I am getting only 2. If it is 2 coins, I am getting 4. So I need what? Minimum of 3 coins, right? Of course, if you see somewhere you may have overlap also. TTH. Okay. So you have totally 6. You need 3 coins, meaning 2 power 3, 8 possible states you will get with coin. So I need only 7. So 3 coins I require. Whereas dice, if a single dice, I have 6 states, but totally there are 7 states I require, so I need 2 dice. So meaning what? Meaning what actually you are getting? With the 3 coins, I am able to represent the colors of a rainbow, or with the 2 dice, I am able to represent the colors of the rainbow. But in fact, I have some more states. It's not that I have exhausted the states of dice, right? Right? So meaning what actually? A coin carries less information than a dice. And it takes 3 coins to distinguish 7 colors, whereas you require only 2 dice. Okay. So now where this is getting correlated with what so far we have learned, we said qubit, a single bit. Single bit is having two states, 0, 1, right? So imagine if I am representing this information with a classical bit, how many bits that would I require? Imagine if I am going with a quantum, what is that I would require? So something with the two states carries the smallest amount of information possible. That is the classical bit. And if you add more states, you can carry more information. From where we are getting more states? Because of the qubit. Okay. So the essence is that underlying principles of mathematics, as professor was asking in the morning, sir, these principles of linear algebra, complex numbers, these are all there. But then why we are going for quantum? Because of this. Because of this means what? We are able to identify some structures. So in fact, the example I have shown is the dice. Okay. So we are able to implement some structures, physically realize some structures that can carry more number of states. What are those structures? Qubits. Sir was mentioning how these qubits can be implemented. There are various models, right? Photon based models, then electron spin based models. Like that, there are models people are able to build. And because of that only, we are able to get the power of quantum computing. Now, again, to carry out that particular discussion, what morning was discussed, is it that only we are having this advantage? Certainly not. We are able to perform calculations moving from real numbers to the complex numbers. So yesterday morning, yesterday afternoon, today morning, what so far you have seen, rather than the real numbers, everywhere you are finding the complex numbers, right? In fact, a real number itself is a complex number, right? Where in which your imaginary field is 0. So actually, we are dealing with the complex numbers. Even in the real world also, we are dealing with the real numbers which are complex, but we are nullifying that imaginary value. And because of that, we are saying real numbers. Right. Anyway, so the quantum computing or mechanics is different from the other branches in the way we are using the complex numbers. Okay. Of course, complex numbers are already there in the various applications, but how we are using to represent the state of a qubit. Okay, that is where these numbers. Then from single state to the superposition states. Yesterday was discussed, morning also was discussed. So from single state, we move to the superposition states, right? So every object exists in a unique place and in a well-defined state, even when we are not looking at it. That is what in the classical thing. So meaning what? You keep some object stored, even if you don't observe it, it will be in the same state. Whereas in the quantum, it tells us that it is false for objects that are very small. Meaning what? Small kids what? If we don't observe, what they do? They do naughty things, right? So they will not be in the place. So if you ask them to sit here and then do, no, they will not sit. They will be doing a lot of naughty things. So it's like, so when you go to that, for that small thing, what was the technical terminology they said in the last 2 days is subatomic level, right? Microscopic level. When we go to that level, objects will not be in a well-defined state. Rather what? They will be in a doing some activity, right? And because of that, we are saying that we are moving from single state to the superposition of states, right? It is simultaneously in being in multiple states at the same time. But what is the interesting aspect of it? The moment you observe it, they will come to a state, which we call it as collapsing to one particular state, right? And we call it as a measurement. So when you don't measure it, when you don't observe it, they will be in multiple states. But the moment you observe it, they will come under one particular state. So to give, since all of us are computer science, to give a analogy, we know that fuzzy logic, right? So fuzzy logic, what it is, given an object, you define a membership function, then what happens? I am in a membership, I'm in a fuzzy set of, even in engage, I can belong to a fuzzy set of kid, but with a membership degree 0, right? But with the membership degree 0, I will be in a fuzzy set of, say, middle age. So I am being in multiple states. So I can give an analogy to a fuzzy logic, wherein which I am there in multiple states. But when you measure it, so it comes under like, kind of a defuzzification. I'm just giving a crude example, right? Then we move from locality to the non-locality. Okay, best example, in operating systems, we deal with algorithms. We know that, a memory unit that is visited, it is most likely that the processor may visit, if you visit an ith location, you may visit I plus 1, I minus 1. But, whereas in quantum, you move from locality to the non-locality, wherein which, if you look at all classical science, objects are directly affected only by nearby objects. As I said, in operating system, we deal with the scheduling algorithms, right? So based on this particular philosophy. However, in quantum, the laws predict certain effects that work in a non-local manner. From where this non-locality is coming, people talked about the entanglement, right? Wherein which objects get entangled. Objects get entangled. The moment you try to measure one, it will affect the other qubit also, the state of the other qubit. So particles can be connected or entangled in a way that action performed on one of them have an effect on the other one. Now the point is, actually locality also affected, it's entangled, but it is about, even if it is the particle is at a distance place, that's what is the beauty of entanglement. And then deterministic laws, we are moving to the probabilistic laws, right? So to which specific state, we said, if you don't measure it, if you don't observe it, quantum state would be in a superposition of multiple states, linear combination of multiple states, if you don't observe. But what is the probability here? The probability comes the moment when you measure it, to which state it would get collapsed is the probabilistic nature. It is not deterministic nature, right? So whether it gets collapsed to the morning Sar was talking about, the computational basis, wherein which you have, on the north pole you have 0 and on the south pole you have 1. When you measure it, it falls to either 0 state or 1 state. That is probabilistic, right? It depends upon to which state it falls. It depends upon your amplitudes, right? So we said, if you have a qubit which is represented as alpha ket 0, beta ket 1, this is my qubit, right? This is my qubit. Then what happens? So to which state it gets collapsed is based on the square of your amplitudes, alpha square and beta square, right? So that determines to which state it gets collapsed. So from certainty to the uncertainty, this is another interesting phenomenon of quantum world, wherein which the laws of quantum mechanics informs us that there are inherent limitations to the amount of knowledge that one can ascertain about a physical system. Based on this, we have a principle. The other day, Professor Balakrishnan was mentioning about Heisenberg uncertainty principle. What is a Heisenberg uncertainty principle says? More accurately you know about a particle's position, the less accurately you know about its momentum, right? When an object has a momentum, if you wanted to determine its position in a very precise manner, how it is possible when you are having a moving train, if you wanted to precisely know what is the exact position of it, how do you know? Because it is moving, right? So that's what is the meaning of it. So the more you know about position, that means you are less calculating about its momentum. What is the example I said is the other way. The more you know about momentum, the less you can tell about its position, right? So and vice versa. And vice versa. From where this is linked, yesterday Professor Balakrishnan was mentioning about the wave particle duality. Light being there in the condition of a particle as well as a wave, right? So these are the features of the quantum world. That is what actually makes quantum computers different and from the classical computers. So again, you can see that here we have a classical bit, and this is your qubit. Of course, morning sir was talking about the block sphere representation. It's a sphere. You can see some dots here. You can think them as the qubit qubits, and you can see actually morning sir was telling about the accurate or exact qubit states and the mixed states. Those things which are not on exactly on the sphere, you can think them as the mixed states. So a qubit can be represented. How you can represent a qubit? By a spin of an electron or polarization of a photon, right? So Sir was telling about in the morning about how to physically realize such qubits. There are technologies to by implementing spin of an electron or by implementing polarization of a photon. After some time, we will talk about quantum key distribution, wherein which you will see in the QKD, quantum key distribution, you will see the qubits are exchanged in the form of polarization of photons, right? So like this, how do you implement them? Because now either Google is doing or IBM is doing, what they are doing is focusing on implementing, designing such qubits, right? So this is the one. So you can see that the electron spin. You can morning sir was talking about the representing in the form of a block sphere. Of course, it is a single qubit. So spin up, spin down. It's not only spin up, spin down for as an electron shown here, but it can have multiple states, right? So this is through electron spin up, spin down notations. And of course, you are having, as I said, photons being implemented as a light polarization through horizontal polarization and vertical polarization. Okay, so both would be used while sharing the key distribution. So in cryptography, one of the important problem is how two users, Alice and Bob, will have the common key when they wanted to interact in a symmetric encryption algorithms like AES. So people so far have used asymmetric algorithms such as RSA, Diffie-Hellman, elliptic curve to exchange the key. But quantum computers are breaking those algorithms. And because of that, now people are building qubits which are transmitting the information through polarization of photons. So you carry the information through polarization of photons, and hence, key can be exchanged. The beauty of such polarization is that the moment you send the qubits or the key in this way, either horizontal way or vertical way, if suppose an eavesdroppers listen to this, what happens? You are actually measuring the state. When you are measuring, what happens? The qubits comes to a particular determined state. So meaning you are collapsing the qubit state. So once if the qubit state is collapsed, both Alice and Bob will be able to know that there is an eavesdropper. Generally what happens? Eavesdropping is a passive attack. Meaning what? You do not know who is listening to the communication channel because somebody is there listening to this channel. Now imagine somebody is listening to our conversation beyond the wall. How do you know? Until unless you go and see and outside. So it's a passive attack. So when you implement this exchange of information through this, since you attacker measures it, what happens? It gets collapsed. It gets collapsed. Both Alice and Bob would know that yes, Eve is listening to that. That is one thing. Second thing, morning Sar was talking about the no cloning theorem. Meaning what? Attacker wants to copy this. He cannot copy because the quantum states cannot be cut, copy, paste business is not there. Right? So that's the beauty of this one. So sir, now if you see here, collapsing, when I say it is the general usage term. In a quantum, we are saying it is a measurement. When I say measurement means what? When I measure this a qubit, it falls under either it belongs to the 0 state as it was shown at the north pole, or it comes to settle down at the south pole. Okay. So to which pole it settles down, it determined by your probabilistic amplitudes. So the meaning of collapse is nothing but settling down to either a 0 state or a 1 state in your Z axis. Morning Sar was mentioning about Z axis, right? So this is Z axis. Now you have multiple axes. When you take it as a 3-dimensional, you have X axis, Y axis. This is computational basis, 0 state, 1 state. You have Hadamard states, right? One is called plus and then minus. Your measurement can settle down to this also. This is called your X basis. Now you have Y basis, wherein which you have positive Y, negative Y. Your measurement may settle down to this also. Sir, it is not that why I should take Z basis, X basis, Y basis. I want to have my own basis. Of course you can have. So this is my A basis. This is my AB basis. If you want to measure it, you can define your own basis and measure it. Because you are having, as Sar was telling in the morning, when you think it as a sphere, you have infinite possible, you are about to ask something. So when I'm sending the information, I'm encoding in the form of qubits and I'm sending it. Okay. When I'm sending the information in the encoding in the form of qubits and I'm sending it. So when I'm sending it in the qubits, the other receiver, see, I have my 0. I want to send 0. In a classical channel, you will send 0. In a classical channel, you can send 1. But in quantum channel, I take 0, I encode it into the qubit, then I send it. And the receiver will take it, decode it, and get the bit. So now, what happens in this quantum channel? If the eavesdroppers listen, he is measuring that qubit, right, to get 0, 1. That will be known to the both communicating parties, because you are disturbing, as I said, you are collapsing from quantum state to classical state. When we discuss this, which one, sir? Correct. So when you take a superposition state, when you take a normal bit, you apply Hadamard, you get the superposition. When you apply Hadamard again, you will get into the classical state. Which classical state? We do not know. Which classical state? We do not know. That is one thing. So once the eavesdropper listen to that particular bit, okay, so the people, you are disturbing the quantum encoding, right? Once you disturb the encoding, then the either sides, it becomes like in your interruption, right? See, we are talking about interception and interruption. The moment you are measuring it, you are doing interruption. When you interrupt, what happens? Your attack will be like an active, so that what happens? Your both sides will know about it. Okay, that is the beauty of this the QKD part. That anyway, while talking about in the upcoming these things, we will see. So correct. What I said about the no cloning is, what you are talking is after measuring it. I am saying before measuring it. When it is in the quantum state, can I copy? So it is this. When we will discuss the no cloning theorem or no cloning this thing, and then we will prove that when I have, see, what do you mean by copying? Imagine that I have two qubits, X and Y. X and Y. What is meant by copying? I want to copy, see, what happens in our, you are copying this information to that, right? So I want to copy the state of this to this. Is it possible or not? It says it is not possible. Why it is not possible, we will discuss. What is your question? Sir, I have measured it. When I measure it, what becomes is your classical, right? When you measure this, after classical, you can copy. When it is classical, you can copy. As long as it is in the quantum, you cannot copy. We are applying the quantum. Yeah, I will show. Okay, see, it is this. It is this. The proof is this. Okay, I want to copy from X to Y. I have something in X. Okay, that I want to copy. When I copy it, what I will get here? Something is theta. What I will get here? What I will get here when I copy it? I have theta and X. When I copy in to Y, what I will get? Theta, right? I should get theta. How? When I will get? No. Measuring is different. So when I will be able to get? I am saying copying. For quantum, any operation is what? Yesterday morning, sir was talking about unitary operator. You need some operator. You need some operator U, which will take your state of X and copy and put it in the qubit Y. Okay, what operator we have? Another qubit, replicate, copy. Because see, what we are seeing is control C, control V is the naked eye. What happens inside? There must be some operation. What is the operation for quantum? It should be an unitary operation. What is that unitary operation? Sir was talking about Hadamard gate, Pauli X gate, Pauli Y gate, swap gate, T gates, control Z gates, C naught gates. What gate we have? What operation we have? We have nothing. Since nothing is there, it is not possible. Okay, that is what is the theorem says. Correct. No, that's what madam is. That's what I'm trying to, this one. See, I'm not saying measurement here. Where I said measurement, see, I have a qubit with some information and I'm copying it to another qubit. Copying means some operation, some operator. So if I have an operator which can copy it, what will happen? And do we have such operator? See, it is like this. Sir, it is like this. It is like this. See, in logic, No. Yeah, in logic, we have multiple forms of logic, right? Deduction, abduction, inference. What this logic says, no, you say something, okay, and you prove that. You prove that. What is that saying? I have two qubits x and y. Okay, I have two qubits x and y. I want to copy x state to the y state. Okay, and for that I require an operator. That operator is u. Now you say that there is no operator, then what does it mean? There is no operation. When operator is not there, how the operation will come? Okay, I think then I will show first the theorem. Yeah, sir, that if I get the, if I get the, if I get this another, no, I think better I will start that first, then, because of the curiosity. Hmm? Uh, Correct. See, because why it is not possible? Because you don't have the, because you didn't have the operator. Correct. There is, since, why, when you say it is not possible, why it is not possible? Because there is no operator. Okay. So now let us say, imagine, I'll just, because of this curiosity, I will just go with this. Okay. So let us see this. We'll just directly go to that no cloning. So let us see this. Okay, I have an operator u. Okay, and this is first one is my the original this one. The second one which I wanted to copy, to which I wanted to copy. What would be the outcome of this? If I have u, what would be outcome of the first one? What would be outcome of this? If I have a u, what would be outcome of that? Get 0, and which is copied to the second one. Similarly, when I have the operator, why only 0 I want to copy? I can copy 1 also, right? So if I have an operator, now what theorem says is you don't have a u. Okay, so now let us see this. The interestingly, this goes this way. Now imagine I have a qubit. Okay, and we know that when qubit is represented, then square of its amplitudes would be 1. So I have a qubit. I have a qubit, which I'm calling it as a psi, and alpha ket 0, beta ket 1. Right from yesterday, we are seeing this, wherein which their probabilistic amplitudes, when you square them, you get the 1. This is the condition. Now, the question is, do we have a u so that I take my qubit and trying to copy to the second qubit so that what I get? Correct? Correct? So that's what I have written here is I have written it in the form of general form. Now let us see what happens. Okay, see this. Okay, so I have a qubit psi which is alpha 0, beta ket 1, and probabilistic amplitudes alpha square plus beta square is equal to 1. Now, what is the question we have? Do we have an operator u so that when you apply the operator, the qubit state gets copied to the second qubit. So meaning what I should get is, when u is there, what I should get is the output as get psi and get psi, because I have copied it, whether I'm getting it or not. Now you see here, what is when I expand this, my LHS, when I expand my LHS, what is left hand side? Operator over qubit and the copying bit. So what is psi? Alpha ket 0, because I have written here, right? Beta ket 1. Now my theta is same. So now let me expand it. So I take alpha out, u over ket 0. What is when I apply this operator, what happens? It is nothing but your tensor product, right? So ket 0 tensor product theta plus beta over beta with operator u over 1 tensor product theta, right? So what I have done is, I have just expanded it. I took my LHS, expanded it with the definition of the qubit, and then I'm writing this XR representation in a simple form like this. Okay. So now what I'm supposed to get? What I'm supposed to get is this. What I get is, when I will get this, when I will get that, so I can further simplify this. Why I have simplified in that way? Why I have simplified in this way? I have written ket 0, ket theta as 0, 0, ket 1, ket theta as 1, 1. Why I have simplified? What is there on that very top? What is there on the very top? U over 0 theta, I should get 0, 0. U over 1 theta, I should get 1, 1. That's what. U over 0 theta, I got 0, 0. U over 1 theta, I have 1, 1. Right? So what I am supposed to get and what I am getting. So this is what actually no clearing theorem says. We could have got this, but we got this. Okay, because there is no theorem says there is no operator u that gives you this. Okay? There is no operator u that gives you that, and hence there is no way that you can copy. Okay, so I hope you guys you are able to follow. So the first one we said you have an operator, then you supposed to get 0 theta 0 0, 1 theta you should get 1 1. So what we did, we took a qubit, we tried to copy it. If we copy it, we will get this. We should get this. But when you expanded it from the LHS, what we are supposed to get RHS is this, but what we get is this. Okay. If at all there is an operator U, we should have got this. This is the RHS. Okay. Repeat, sir. What is that? Okay. No. If it is this way, fundamentally that itself is insecure, right? If I know what is your OTP or what is your 4-bit PIN, you save it, that ATM card, whatever is the locker, whatever you are creating the information. If I know how, we are talking about what? We are talking about securing the channel. Okay. In QKD, you talk about securing the channel. If there itself, fundamentally in generation itself, if it is lost, that's what, if insider is there, insider attack, who will do? We cannot. Okay. So this is what is no cloning theorem. But anyway, we will discuss that, this one. So again, these are all about features of the quantum world, where in which are the multiple representations. You have 0, 1, whereas in the case of quantum, we will have the spin of the electron take care of your qubit these things. So again, because of that, what happens in the case of classical, you need 0 0 0 1 1 0 1 1 goes in a classical sequential fashion, whereas in the case of quantum, you can have all together of 4 possible states at a time available. That is what is the quantum speed up, that what we get. Another interesting thing about the algorithms, probably tomorrow algorithms would be discussed, where in which when you look at the classical algorithms, Sir was telling that he is going to handle design and analysis of algorithms, right? So you may be talking about in the class about the algorithms that are to be solved in a polynomial time, meaning what? Problems that are solvable by a deterministic classical algorithm in a polynomial time. And in this algorithms, you don't expect any kind of an error to be there or randomness is being involved, and classical algorithms like sorting, multiplication and all that. Whereas in the case of quantum, the algorithms what people deal is called BQB algorithms. What is meant by BQP? Bounded error quantum polynomial time. So here what? It's not simply polynomial. People say P is a subset of BQP. P is a subset of BQP. So meaning what? The algorithms that the quantum computers deal are much more larger in the case of complexity, right? These are all the problems solvable by quantum algorithms in a polynomial time, bounded with error. Okay. So Sir was telling about from where this error is coming, because of the your decoherence, because of your measurements and all that, you can bound to get the errors. So I cannot say a problem where in which I should have a deterministic this thing and expect a algorithm that is probabilistic in nature to give a exact solution. That is not possible. And here you are having a probability of having the correct result, meaning of greater than or equal to 2 by 3. Meaning what? You need to have some bounds. Okay. Meaning what? If I have my error rate out of 3, if I am getting 2 times correct, it is fine for me. That's what is the probability of correct result should be greater than or equal to 2 by 3. And this error, see, I think morning Ganesha sir was telling about, in neural network learning, what we do is we actually learn in a way that your error rate comes to 0. But if you see, there would be a point where in which this comes to a particular epsilon value, that epsilon we aim for to be 0, but it will not. So we say that epsilon, to a particular point of error, it's okay. So it is like that. We try to reduce it. So where this type of algorithms are there, especially in the integer factorization, which is Shor algorithm that we will discuss, if not today, maybe on the 5th day. Then unstructured search, which is the Grovel algorithm. Also, these are the type of algorithms. So again, I'll not spend time on this because already these things were discussed. It is deterministic, whereas here it is quantum Turing machine. Type of algorithms are deterministic. Here it is probabilistic, and you have a no tolerance of error in the classical environment, whereas you are having some tolerance towards the error, and your time and space complexity we see here. Whereas when you are measuring the algorithm, it is about your superposition parameters such as entanglement, interference, and etc. And type of problems, what we do is typically sorting kind of a thing. Here this is different. And as I said, polynomial time algorithms, which is a subset of BQP, bounded quantum error polynomial time algorithms. So this I will skip. So one of the interesting, okay, so if you see here, one of the interesting problem that the quantum you can see in the literature also is about integer factorization, I said, Grover search algorithm, I said, and another interesting problem is called Simon's problem. So let us see what is Simon's problem. I think this is not moving. This is not. What is Simon's problem? Imagine that I have three bits or 3 qubits or whatever it is. So I have 2 power 3, which is 8 possible states. So I'm just trying to map an input of 0, 0 to ABC, and similarly input 1, 0, 1 to ABC, 0, 1, 1 to XYZ, 1, 1, 0 to XYZ. I'm not giving, or we don't know what is this mapping. You can think like it as a kind of a oracle, wherein which you don't know what is this particular F, which is mapping your input to the output. Okay, but interestingly, you can observe something in this particular output. Is it working? You can observe something interesting here. What is that interesting aspect here? If you see here, 0, 0, 0 and 1, 0, 1, it gives the same output, and 0, 1, 1, 1, 1, 0 gives the same output, and 0, 0, 1, 1, 0, 0 also gives the same output. And the pattern, what we observe is here, each pair is distinguished or differentiated exactly by 1, 0, 1. This is called the period. And how to find that particular period? We represent that period as C. In same you can find when we are talking about Shor algorithm also, finding the period. So this particular finding C, what is that C? What I want to find here is these pairs of input which are mapped to the same output, those pairs to how much they are differed. You understood the problem? I repeat, you have some input and they are mapped to some output. How they are mapped, let us not worry. That mapping of F, let us not worry. We need not worry about this F. Okay. We are not interested in what is that F. What is that we are interested in? When you know when you give some input, when there is an output, there are certain bits which are mapped to the same output. So these two are mapped, these two are mapped, these two are mapped. And what is the pattern we are observing? Each pair of this, they are different by exactly by 101. Okay, and how do you find that particular pattern of 101 or the period called C? Classical, what we should do? Pattern, yes, this particular difference, where in which each pair is exactly differ by 101. That difference, that 101, how do I find? We try all possibles, right? All possibilities. So what we are going to do? We are going to have the following requirements on F. So F000 is equal to F101. That's what F00 is equal to F1001. Again, I repeat, don't worry about what is this F. Don't worry about some arbitrary function. This is my requirement. Okay. So what is that we are going to find? We are going to find the difference of 101. Okay. So for this, we need to try all possible combinations in a classical scenario, one by one. So to find C, a classical computer would have to try all possible combinations of inputs and outputs and match for the what is the pattern. Okay, which requires an exponential time of trial and error, 2 power n. Okay. However, in the case of quantum computer, you can put everything in the form of a superposition, and at a single stretch, you can go and identify what is the pattern. And for that purpose, we need to go for Fourier transform and phase estimation. These algorithms need to be there at the back, and then implement the superposition and get the period in a single phase. Shor algorithm also finding the period again in a single stroke. Okay, there that period is we are going to find in Shor algorithm the prime factors of a given integer. If you observe in RSA algorithm, we are going to find what is the complexity of RSA algorithm on which given an input. So typically we all know that imagine I have two numbers x and y. I can easily calculate n, which gives me which is coming from x into y. This is always possible, right? But imagine if I give n, if somebody is asking you to find what is x and y, becomes first one is the problem of finding the product of two integers. The second one, this is finding the product. This is very easy, right? What is this? Finding the factors. So finding the factors. This problem is finding factors. So finding factors becomes tough. First of all, it is tough. And not only just simply factors, but we are trying to find the prime factors. Right? So the Shor algorithm is able to solve it in a way that you are finding the period. Okay. So that's what is the the Simon's problem. Another interesting phenomenon is called, quantum computers violate Church and Turing thesis. What is the Church and Turing thesis says? Any problem can be solved efficiently in the real world, can also be solved efficiently on the classical computer. That's what is the thesis statement. Turing thesis statement says any problem that can be solved efficiently in the real world can also be solved on the classical computer. What is this problem? Is it a solvable problem or a non-solvable problem? It is solvable problem, but that's the problem. That is the point. This is solvable on a classical computer? On a classical computer, for the numbers of magnitude 300 digit, not simple 23, 45, 51, 300 digit. Is problem solvable? Yes, it is solvable. Solve it? No. So that's what thesis fails and quantum works. So quantum violates Church and Turing thesis, which says that any problem solved efficiently in the real world can also be solved efficiently on the classical. Classical computers are powerful enough to simulate any realistic computation. That's what is the Turing thesis says. However, classical computers can do everything efficiently. So, the breaking of Church and Turing thesis happens with quantum computers. These are classical, this one. So, another thing, some of the questions that typically students ask, because we handled the class, student ask. Even I think somebody has also asked. Classical computers operate on bits, quantum operates on qubits. What are the consequence in terms of computation and storage? If you see, classical is 0 or 1, quantum is a superposition. So because of that, what is the consequence? It represent and process efficiently many states in parallel. I said in the very beginning, why we are able to represent many states. I gave an example of coin, dice, right? And many states in parallel, right? So, okay. So again, what are the some results that this one? Okay. Another interesting people think, sir, superposition means I'm doing things in multiple parallelly. So is it that parallel computer? I run multiple threads in Java. I run multiple threads. Can I say that I'm my classical system with multiple, the parallel computations? Can I call that as the quantum? Certainly not, because that is behaving with the quantum properties of especially the superposition, entanglement, interference, and measurement. Is it these properties are there? If they are not there, they are not quantum, right? Of course, you are having the property of doing in parallel, but that is different. Again, P is subset of BQP. Okay, what this implies about the power of quantum computers. P is subset of BQP, meaning anything a classical polynomial time algorithm can also be executed in quantum. But the reverse, no, right? So quantum computers are at least as powerful as classical ones, efficient, because they are able to perform various tasks using suitable quantum gates, right? But it also is able to solve, because of these properties, other problems which are not, right? Similarly, sir, I have a probabilistic classical algorithm. You are saying that this is probabilistic, the output is probabilistic. My algorithm, classical algorithm, is probabilistic. Okay. Let us take one example, random number generation. You generate random numbers probability, right? You don't know which random number you ask. If we ask students, how do you generate random numbers? Sir, there is a function. What was that function? Rand function. So it generates. But how it generates? So we call those random numbers generated by classical computers as pseudo random numbers, because they are not true random numbers. Whereas in the case of quantum, that is also probabilistic to generate, but with pseudoness. It's not true randomness, right? So the probabilistic classical algorithms are pseudo random in nature. Now, if you see in the market, which are the startup companies which are coming out with the quantum related products, they are all doing what that they are doing is they are generating quantum random numbers, which are truly random numbers. Unlike your random numbers created by these classical computers, which are pseudo in nature, the companies which are there in an Indian startup scenario, they are generating quantum random numbers, which are truly quantum random numbers. That is the difference between the probabilistic classical algorithm, the algorithm that we have in the quantum, right? This I will skip. Morning sir was talking about this. You can see this. You can see this, the superposition part. Just observe that image. can see. So 0, 1. Yeah, so it is, so 0, 1, your Z basis. And then now you are having X basis, Y basis. You can see the, the qubit state, right? Qubit states. So probabilistic amplitude of 0 is this, then you can see the multiple combinations, right? And similarly for ket 1, the probabilistic amplitude is this. So they get changed. So now you can also see, the sir was talking about the polar angle and azimuthal angle. So this is your, yeah, this is your polar angle and this is your azimuthal angle, right? So that's what morning sir was talking about through block sphere. So this is just wanted to show. So okay, so this I will skip. This is the one. So you can see that, your block sphere, that what we have just now seen. So Z axis, X axis, and then Y axis. This is your Z axis, 0, 1. You have your X axis superposition. This is your imaginary Y, which is giving you the phase shift. I was talking about phase shift. So this is your X superposition. So what is phase shift is this you are shifting with a phase angle. Okay, the shift is the phase. Okay, because of that you are able to get another basis or another axis called Y axis. So X axis, which is a superposition, Y axis is also a superposition state. But what is the difference? You will have a, what is the difference? Phase shift. So the phase gets shifted. Okay, that's what is the difference. Okay, so you can see that, if you have a, this is, we saw that Z axis, then you have an X axis. So imagine that you have a point here. So what is that point? 1, 0, 0, where in which the block sphere, that point intersects at the X axis. Similarly, you can have the point here also, right? So what is the point here? So 1 by root 2. So this is your superposition, and the other side of it is the minus superposition, right? So minus, this is plus, which we call it as plus, and this becomes minus, right? So this is at the point minus 1, 0, 0, right? Again, these are all for the single qubit, right? Now you see here again the Y axis, and then this is the other side of this. So now you see the difference is the phase shift. Phase shift. Now you are getting the phase difference. Okay, especially the phase angle is getting with that I. Okay. So now you can say that this plus is 1 by root 2 ket 0 ket 1. What is this called? Superposition state. This is negative superposition state. This is the complex I superposition state. This is the phase shift of minus. Okay, this is at the block sphere. So there are many possible states. Now, why only these states? As you see that block sphere, you can find n number of points. Not only these points, you can have n number of points. So this is another representation. You can see that you can take any number of points, n number of points, possible states, right? If somebody asks what is the number of, you have numbers between 0 and 1, infinite, right? So kind of a thing. Right. So it is not restricted to equator. You can have multiple, right? You can see 1 point here, which root 3 by 2, ket 0, 1 by 2, ket 1, this point. So a qubit can be in any point on the block sphere. That's what actually we have seen. Okay. So when you are having this, so far we said measurement collapses the qubit. Okay. Now measurement comes, one of the interesting aspect which I thought I will discuss here is that you can measure the qubit in any of the bases. Okay, so you can see that quantum measurement collapses the qubit superposition. That's what we said, alpha square plus beta square into one of its basis states. Okay, with the probability equal to the square of its amplitude. That's what we have written here. And remember, measurement is No, square of alpha and square of beta. No, root 3, 3, and no, 4. You take LCM, right? Yeah. So root 3 by 4, 1 by 4, 4 by 4. Okay. So measurement is irreversible. Okay. So now that this point I thought I will discuss because how do you measure in multiple bases? Okay. So measurement collapses quantum state to a classical outcome. This is all we've discussed. Okay. So upon measurement, what happens? Your zero state, whether you will settle into the zero state is decided by alpha square. Whether you will settle into the qubit state of 1 is decided by your beta square. Okay. So now imagine I have a qubit which is in the superposition state of both 0 and 1. Now the superposition is equal. So measurement has the chance of getting 50% 0, 50% 1. Now imagine if my qubit is having a superposition for 0 as root 0.8, for 1 it is root 0.2. So probability of getting 0 is 80% and probability of getting 1 is 20%. So more likely if you observe more likely this qubit would settle down to 0, right? So now imagine I have the qubit having 0, 0, 0, 1, 1, 0, 1, 1. And you can notice that all are having the equal probability. So 25%, 1 by 2. Okay. So again, I'll come to that point of measuring in multiple qubits. This is about entanglement. I think already Sir has discussed. You have a Bell state, which we call it as the strongly entangled qubits. Meaning what? If you measure one particular qubit, it affects the other qubit also. What are all the such states we have? So you have one particular state called 0, 0, ket 0, 0, ket 1, 1 by root 2 is a strong entangled state, which we call it as a Bell state, right? Similarly, the other states also possible, right? Is it only for 2 qubits? Of course, you can have 3 qubit also being in a entangled state. So this is the strong entangled qubit state with 3 qubits. So 000, 111 by root 2, which we call it as a Greenberger Horn Jellinger state. Okay. Sir, is it that only 2 qubit, 3 qubit? Can I generalize it? Of course, you can generalize it so that you can have n number of qubits being in the entangled states. What is that generalized entangled state of n qubit is given here, right? But typically, yesterday Professor Balakrishnan was telling about that any problem that you can solve with n number of qubits can also be solved with 3 qubits, right? 3. So that's what yesterday Sir was mentioning. You can model it with 3 qubits. So you can solve that with the this one. And then another interesting thing is interference part, which is not, yeah. So that proof, I will leave it for derivation because it is widely available, any of the quantum books. So proof that you actually asked for 3 qubits. Why 3 qubits even for the 2 qubits when I have this particular state of, ket 0, 0, ket 1, 1 by root 2 is a strongly, entangled, meaning correlated or entangled or connected. Measuring will, one you measure it, it disturbs, collapses to the other, is the derivation is there. So these are the, see this one and this particular state and this particular state, these are all strongly 1 by.
Here, alpha will be good.
One or one.
One state is
1 by.
It's a maximally entanglement. The amplitude of the alpha determinant say for maximally entangled state, the amplitude of theta or for that
No, it is because of that only we are getting that alpha beta values like that. Yes, yes, yes. So we'll continue the interference part. The interference part is another interesting aspect. You are having two type of interferences called constructive interferences, excuse me, and destructive interference. Right? Constructive interference, wherein which amplitudes add up. When you are running this I will with this I'll stop. When we are running an algorithm called Grover algorithm, wherein which you need to amplify for a given solution probabilistic value, we actually see the constructive interference. Okay, so destructive interference amplitudes cancel out. Okay, so you can see this interference phenomena in physical world also. So you can see that in various waves in a pond. You can see that when you drop a stone on a pond of water, you will see the waves gets propagated, and initially you can see constructive waves because you will see the waves getting bigger. Then slowly they get one by one they hit each other. That becomes a destructive interference, right? So just this interference effect you can see in the quantum environment also, which we do not see in a classical environment. Okay. Now imagine I am applying Hadamard gate. Hadamard gate, why we apply it? To get a superposition state, right? So two Hadamard gates are applied sequentially on a qubit. We call it as a sandwich Hadamard or Hadamard sandwich. So take a qubit, apply Hadamard, and again apply Hadamard. Okay. So let us take that. Imagine I'm starting with 0. Is it in a superposition state? It's a simple ket 0. Apply Hadamard. When I applied Hadamard, so you were you know that this is in a x basis. This is the x basis. So you were ket 0 when you apply Hadamard, that z basis it gets transformed to the superposition, positive superposition, that is the x basis, which is plus, right? So Hadamard puts the qubit into the equal superposition. Now what we are aiming, actually we are applying two Hadamard gates. So this means you are getting 50% chance of getting 0 and 50% chance of getting 1, right? So the actual quantum state is not 50% classical, it is a combination of 0 and 1 with amplitudes. Now let us see what is this interference. Now let us apply Hadamard again. What I said earlier, we are applying Hadamard in a sequentially. I took 0, I have applied Hadamard, what I got is this. Okay. If you think that this is actually giving you confusion, just leave this part. This part you leave. I wanted to apply two Hadamard gates. So I am taking a qubit 0, ket state 0, applied the Hadamard, I got the positive superposition. Now again I am applying Hadamard. Okay. On what I am applying Hadamard? The plus state. If you remember this plus, right? This is this plus. So applying Hadamard on this. So when I applied Hadamard on this, what happens? So 1 by root 2 Hadamard 0, 1 by root 2 Hadamard 1. This is clear? I repeat. Hadamard over 0, I got superposition. Next. So on the superposition, again I am applying Hadamard. So 1 by root 2 Hadamard 0, 1 by root 2 Hadamard 1, right? So what is that when I take it out? When I take it out, what I am getting here is that Hadamard 0. What is meant by Hadamard 0? 1 by root 2 ket 0 ket 1. What is Hadamard 1? 1 by root 2 ket 0 minus 1. What is that minus 1? If you remember, this is plus and this is minus, right? So now what happens? Now what happens? What is the output I am getting? What is the output I am getting? So 1 by 2 ket 0 1 0 minus ket 1. So minuses gets cancelled. So I am getting ket 0. So what is the final state I am getting? Ket 0 with 100% probability. What happened to my 1? It gets nullified. Earlier what happened? 50% classical, sorry, 50% 0, 50% 1. When I applied Hadamard again, I am getting with 100% certainty ket 0. Okay. I started with ket 0. I applied Hadamard. I have got this. Again, I have applied Hadamard. That's what I went, right? Okay. And what is the output I got? Final state is ket 0. Whereas here, I got the probability of 50% of 0, 50% of 1. Now I am getting final state 100% with 0. Now imagine if I start with 1. If I start with 1. If I start with 1. So apply Hadamard over 1. Apply Hadamard over 1. What I get is 1 by root 2, this state, 1 by root 2 ket 0 minus ket 1. This one, right? Again apply Hadamard. What is that you get? So if you observe here, just this you try out. So especially if you observe here, my ket 1 is nullified, which I am calling it as destructive interference. Ket 0 amplitude is doubled, which I am calling it as constructive interference. Right? Madam? I say, observe this. Actually, ket 0, if I have applied only Hadamard, I am getting output of ket 0 with 50% probability, output of 1 as a 50% probability. No, I don't want that. I want compulsorily 1. Sorry, I want compulsorily 0. So what I should do? Apply again Hadamard. When I applied again Hadamard, what happened? My 1 is getting nullified. Okay, this is called destructive interference. My output, what I want, that particular output amplitude got doubled. That's what called is constructive interference. Where this will come into picture when you discuss Grover algorithm, which is a kind of unstructured algorithm. In fact, I was looking for how to teach Grover algorithm. One of the beautiful example I have found is like, imagine look, there are about 20 people here, 40 people here. Okay. Let us say all of us at a time, all of us, let us say V80. Please say V80, V80. All of us said V80, right? Now, imagine we have captured this. I wanted to identify, imagine Ganeshan sir said V80. I want to identify his voice. That is my job. How do we do in a classical environment? I repeat, there are about 40 people in this room. We all said at a time one particular thing. We wanted to find out who said that. Okay, kind of unstructured search. Similarly, look at, say, take an example. For this case, what we need to do? We need to know his voice modulation and amplify it. Rest you have to nullify it. Okay, so constructive interference and destructive interference, you will see that when you are talking about the Grover algorithm, because with this, at a time you can do. In a classical scenario, you need to search for everybody, like what we have done in the case of which problem? Few slides back, we said one problem. Huh? One problem in the very beginning, we said Simon's problem. Simon's problem, right? We have tried with, we said Simon's problem can be solved, that period finding can be solved using superposition, interference, so that this same interference. Decoherence, I will just skip. This also I will skip. Polar forms are, yesterday I said about polar form of the complex numbers. This also I will skip. Maybe we will take this are discussed in the morning, so I will just skip this. Now this I will talk when we are going after break. We are coming after break. Huh? Yeah, இது கிளியர் பண்ண முடியல, ரைஸ் ஆகல. இது ஈஸியா போகலாம். Okay, so we will continue. What I will discuss now is the measurement. You may wonder, sir, the measurement already we discussed. If I measure it, it comes into the the state of as it was written here, a 0 or a 1 state depends upon your probabilistic amplitudes. There is something beyond that. என்ன ஆஃப் ஆயிடுச்சு, ஆன் ஆயிடுச்சு, வந்துருச்சு. Yeah. So now how I am going to measure it? Okay, I can measure in multiple bases. Okay, what so far we discussed is measuring in the computational basis. Okay, what is meant by measuring in computational basis? Whatever we discussed so far, whether it falls under 0 state or 1 state, is measuring in the computational basis. That means Z basis. I can measure it in X basis, I can measure it in Y basis also, any given qubit. How do I measure it? So a set of distinct measurements outcomes is called basis, right? So you have Z basis with 0, 1. You can have positive superposition, means plus, wherein which you have 1 by root 2 ket 0 ket 1, and then minus, which is the other side of the X basis, 1 by root 2 ket 0 minus 1, which is X basis, and I have Y basis, wherein which I have 1 by root 2 ket 0 plus I ket 1 minus I, which is the other side of the Y basis, 1 by root 2 ket 0 minus I1. What is this plus I and minus I? Is the phase. Okay, this is called phase, a phase shift. Okay, so I have multiple bases like this. I have Z basis, wherein which I have 0, 1. I have X basis, I have plus, minus. So you have Z basis, wherein which you have ket 0, ket 1. You have X basis, you have the measuring states plus and ket minus. You have Y basis, wherein which I have plus I, then minus I. Okay, given a qubit, I can measure it in any of these bases. So 0, 1 is called the Z basis, plus minus is called X basis, I minus is called the Y basis. Okay, now, so what is the basis now? A basis is a pair of directions where we can measure the given qubit. Okay, so now imagine I have 0 state and then I have 1 state. I have 0 state and I have 1 state. What is 0? I am writing in the form of vector representation, or I am writing it in the form of a column matrix. So 1, 0, ket 1, I am writing it as 0, 1, right? I am writing ket 0 in the form of column matrix, ket 1 I am writing in the form of column matrix. Again, yesterday also, I think Balkrishnan sir said, Ganeshan sir also said in the morning, it is all about the representation. You can have vector representation, you can have matrix representation, you can have block sphere representation. When you read the literature, we get bombarded multiple people using multiple representations. Okay, so we need not worry, because we know all of these representation, we can understand very easily. So ket 0, 1, 0 and ket 1 is 0, 1. What do you mean by measuring this particular qubit in this particular Z basis? When I am measuring means I am asking whether the qubit is in the state 0 or whether the qubit is in the state 1. That's what is the measuring the qubit state. Similarly, what about X basis? X basis means we have seen X is, you have plus minus. I have also written here for your convenience, plus minus. What is the gate representation, which is the superposition? 1 by root 2 ket 0 and 1. 1 by root 2 ket 0 negative phase 1. Right? So this we have discussed yesterday, today also. This is your X basis. How do you get it? By applying, Hadamard gate, you can get the superposition states. Now, what do you mean by measurement in X basis? Measuring in Z basis, you are asking the qubit, are you in 0 or 1? Measuring in X basis, you are asking, are you with plus or are you with minus? Because the basis in which you are measuring is X basis. So you are asking the question whether the qubit is with plus state or the qubit would be of minus state when you measure it. Okay. Now, what would be the measurement in Y basis? You are asking the question plus I or minus I, right? So measurement in Y basis is the answer whether the qubit is aligned with plus I or minus I. So measurement means you are measuring in which basis? Okay. I think yesterday or today morning, Ganeshan Varsar was giving one beautiful example. What are your marks? What is your grade? Okay. Actually, you are doing measurement only, but the basis for measurement is there, it is the marks, and here it is the grades. In a similar fashion, you can think you are measuring the qubit in the X basis, you are measuring the qubit in Y basis, you are measuring in the qubit in the X basis or Y basis. Obviously, the question is different. When you are saying I am measuring in the qubit in the X basis, the question is different. The measurement in the Y basis, question is different. So now imagine I am having 0. I am having 0. So I am starting with qubit state 0. I am starting the qubit state 0. So what I am doing is measuring it in the Z basis. What is the question I am asking? If I am measuring the qubit in the Z basis, what is the question I am asking? Are you 0 or 1? So what was started? Ket 0. What would be the answer? What would be the answer? So the answer is qubit is already in the state 0. Is it in the superposition state? It is simple qubit 0. So when you measure it, what you will get? 100% result, which is 0. Okay, 100% result 0. Now I have ket 0. What is the basis I am measuring? X basis. What is the question I am asking? Are you in plus or minus? Are you in plus or minus? What is the question when I asked here? My qubit is in 0 only. When I am measuring, I am asking the question, are you in 0 or 1 when I am measuring it in the Z basis? Now I am measuring in the X basis. My basis is changed. My question is, are you with plus or minus? So now what happens? in x basis, what is 0? What is 0 in x basis? So when you apply 0 in x basis, what actually happen is 1 by root 2 plus minus. Now then 50% chance to get, people, you should get a doubt. I will not answer because you have not asked the question. I am asking the question, how this has come. If I apply Hadamard, what I get? If I apply Hadamard, what I should get? When I apply Hadamard over 0, what I get is this. When I apply Hadamard 0, what I get is this. You are asking the question, I am in plus or minus. So for ket 0, 1 by root 2 plus state plus minus state. How this has come? Huh? Again, Hadamard, actually, madam, Hadamard, you get this. When you apply Hadamard over 0, what you get is this. What is this? When you apply Hadamard, what you get is this. When you apply Hadamard over 1, what you get is this. So the transformation, what you are getting is the Pauli X gate, right? So 50% chance to get plus, 50% chance to get minus. So when you measure 0 in x basis, what you are getting is 50% chance to get plus, 50% chance to get minus. Now I am measuring 0 in y basis. I am measuring 0 in y basis. What is the question? Are you aligned with plus I or minus I? Okay. What is the question I am asking? Are you aligned with plus I or with minus I? How do I represent it? 1 by root 2 plus I plus minus I. Right? What is the operator? Y. So now when you ask this question, measure it, what is the output? 50% chance for plus I, 50% chance for minus I. Now, no, it is about the basis. Your qubit is in some position. Now, in which basis? It is like this, sir. Again, say the point is you are getting very good doubt, but how to answer this? When we are, it is this. You see this bottle, when you see this like this, it is different. When you see like this is a different. When you see like this is a different. Your bottle is same. The basis in which you are seeing the bottle is changing. That's what is the changing in the bottle. Sorry, changing the basis. Measurement change. Okay. So the view that we see, that's what top you see. Z basis is looking from top down. So you are seeing top down. X basis is looking at the qubit from the side. You are seeing it like this. It is X side. Y basis is looking at the qubit and the diagonal. Right? So just for understanding purpose. So again, we are talking in terms of qubit with a single qubit only. Right? If you understand single qubit phenomenon, obviously, we can. Right? So the change in the basis is giving different answers when you are measuring it. Okay. You ask Ashwini Kumar is a good faculty. Yeah, he is not a good faculty. He will not give marks. You change the basis. Again, Ashwini Kumar will become good faculty. He is nice person. You change the basis, right? Person is same. Person is same. Person is not changing. So the basis is changing. Yeah, basis. In which basis I am measuring it? That we will discuss when we are talking QKD. QKD. Otherwise, shall I pass here and go there? No, I'll be happy to answer that, because when you have this doubt, I can answer that. In which basis you measure it? For that, in QKD, what we should do is, in which basis I have measured, in same basis, if you measure it, we consider that key value. If you measure with a different basis, that we should discard. How do you know that what basis and your basis same or not? That we too should exchange. We are not exchanging the bit, rather we are exchanging the basis. That is what is the, anyway, I'll just show. Because anyway, we have discussed no cloning theorem. Now you see, Alice, Bob. We said X basis, Y basis, Z basis. There are two bases. One is called diagonal basis. Another one is called rectilinear basis. Okay. So now what happened? Alice wants to send 0. Alice has used diagonal basis. In the diagonal basis, you have polarization angle 45 degree, 135 degree. She has used 45 degree. Okay. And sent that polarization, light or photon. What Bob did? Bob used what basis? Rectilinear basis. This is diagonal, this is rectilinear. When you measure it in rectilinear, what you get is the horizontal. It could be horizontal or it could be vertical. What you got is horizontal, which gives you 1. What you have sent is 0, what you got is 1. Okay. Now, but you don't know the sender has sent 0 or not. What you should ask the sender is, hey, what is the basis you have used? Now sender will say, hey, I have used diagonal basis. If I say diagonal basis, you will keep that bit. Otherwise, you will discard it. Which one? Yeah, you will get the bit. You will get the bit. See, you will get the bit. See, you will, because bit is same. The basis, your basis gives you the bit. See, polarization angle, can be anything. Because, see, it is like this, sir. It is like this. Say, take an example. You have sent through this. Okay, you have sent this. When you apply that basis, what you get is this only, you will not get this. It is, you think it as a filter. Okay, see, now light is going on. Now you see, I'm putting like this. Okay, imagine I'm putting. Okay, now you see the same philosophy of, you can think that as a filter, or you can think this as the basis. Is that you can think this as the basis. Okay, this is the concept of QKD. So you change the basis. Now you see now interestingly, this communication goes in a quantum channel, but exchange of the basis goes in the classical channel. Exchange of the basis goes in the classical channel. No, this is the key distribution. This is the key distribution. See here, finally you see the key. Okay, This is the bit I wanted to send. I have used the diagonal basis, and transmitted information is this. You have used rectilinear basis, and for that you got the received bit is 1. Like this, next I have sent 0. I have used rectilinear basis, and polarization angle is this. You also use the rectilinear basis, and obviously what you get, the polarization angle is same, and hence the received bit would be 0. Like this, you will get a string of bits. Okay, now string of bits are exchanged. Then what happens? We will talk in the classical channel. I will tell for first bit, I have used diagonal 1. You will check. You need not tell me. You will check, and if both are same, you will keep it, else you nullify it. Yes, you will keep it. Yes, you will keep it. Actually, you should tell me, because I need to know what are the final bits. Now you see 0, 0, 1, 0, 1. Now imagine I need 128 bit key. Now I need to send like this. Okay. Interestingly, if I need 128 bit key, I should minimum send 192 bits like this, because you don't know how many you will drop, right? See, you don't know. You should send more. Okay. And we went with the no cloning theorem, right? Imagine somebody is sitting in between. Now this polarization angles, they cannot clone, copy, they measure it, they get collapsed. That is what is in the channel what happens. Okay. So the measurement of the basis, in which basis you are measuring it, matters. I think we are here. Yeah, so now this is where we stopped. We started with 0. Now imagine, why only 0, 1? I can measure my plus state. Measuring plus in X, measuring plus in Z, measuring plus in Y. Measuring plus in Z, what is that question? Z means 0, 1. So are you with 0 or 1? Since it is in the superposition state, obviously 50% chance to get 0, 50% chance to get 1. Now measuring in X basis, what is the question? Are you with plus or minus? Now anyway it is with plus. So 100% sure to get. Measure in Y, 50% chance to get I, 50% chance to get minus I. Right? Now, sir, I have another qubit. Why you only plus minus? I said qubit can be in any state. So I take a qubit which is in this particular point of the block sphere. Now I can measure that in any basis. So measuring it in Z basis. Measuring it in Z basis. Are you with 0 or 1? What would be the outcome? Now you have the probabilistic amplitudes. For 0, it is root 3 by 2, and for 1 it is, so probability of 3 by 4 for 0, probability of 1 by 4 for 1. Now what is the next question? Again, this particular qubit on the block sphere, where it would be when I measure it in X basis. What would be the question? So what is 0? We know that 0 means 1 by root 2 plus and minus. Get 1, is nothing but 1 by root 2 ket plus minus ket minus. So what we do is we take this and substitute here. So root 3 by 2 ket 0, 1 by 2 ket 1. You solve it by substituting these qubit states. So root 3 plus 1 by 2 root 2 ket plus root 3 minus 1 2 root 2 ket minus. Right? Now what would be the outcome? Probability of measuring plus is square root of root 3 plus 1 by 2 root 2. Probability of measuring minus is square root of. So now my basis is changed, my qubit measurement changes. Okay, the same thing applies for y basis. So root 3 by 2 ket 0, 1 by 2 ket 1, same what we have said with x basis, with z basis, with x basis, now with y basis. What is ket 0 and ket 1 in y basis? So 1 by root 2 ket I plus ket minus I. What about qubit 1? Minus I by root 2 ket I minus minus I. Now you substitute. Yeah, so the probability of getting I is square root of this. Probability of getting minus I is square root of this. Right. So same qubit. My qubit is same. When I change the basis, my measurement is changing. Right? Sir, why only x, z basis, x basis, y basis? I am defining my own basis. Okay, you see here, I am defining my own basis. So of course, line is not there. You can think of that as this. Where? This one? Now tell me what is the doubt? No, this is my alpha. This is my beta. This one? Yes. Yeah. No, sir. No. So yesterday and today, we have discussed that one of the interesting or most significant aspect is this alpha beta values, and what you are handling in the quantum is all complex numbers, right? So what you deal with in the complex numbers, what you have seen is a real number with complex element 0. Now you are seeing an value with the complex element being present. Okay, and another thing. So now take an example. Go to this basis. This is my x basis. What is this basis? This is my I basis. I basis means what? That is having a phase angle from where it is coming because of the complex number. Okay, that complex number, yesterday sir was telling about how the complex number would be represented using the Euler's representation notation, right? So obviously what you are seeing here is the complex numbers. And if you remember the animated image where you saw the block sphere is being rotated, there if you see the rotations, the ket 5, you would have seen that complex numbers also. Generally, when we are teaching our presentations, alpha beta values, we take real numbers and say. That doesn't mean. Yeah, yeah. Yes. Okay, so this is about measuring. So now I will leave this point for your thought, wherein which so far we said measuring in X basis, measuring in Y basis, and measuring in Z basis. I am having my own basis called AB basis. Okay, so AB basis. Okay, so my AB basis, the basis states are these two. Okay, not simply 0, 1, plus, minus. I have defined, or I am taking these 2 qubit points, taking this as the basis. Now you can measure the given qubit state in this basis also. Okay, how to measure that? Just leave it. Those who are interested can try that. Okay, which one? Yeah, so QKD, we are actually, as per the protocols, you are having these bases, rectilinear basis and vertical basis, fixed, the protocols. Channel, right? See, see. Yeah, but yeah. Mathematically, I can talk. I am saying that there is a quantum channel. Suppose somebody asks me, show me where is quantum channel. First of all, how to build that quantum channel, wherein which I set a beam of, as I was telling, beam of photons as my qubit states, and it is. Sir was talking also about this insulation, my channel from the noise. In fact, I didn't tell anything about that. We are all assuming that I am sending the state and he is receiving it as such. No, what about that errors that are happening in the channel? See, our classical channels of internet and all that, this error rates are, almost nullified, right? So what about quantum channel? So people, yeah. That's why the number of, if I need 128 bit key, the number of bits I am sending are more. That is one thing. Second thing is, see, in a classical channel now, you can be anywhere, I can be anywhere, we are able to share. But first of all, establishing that channel itself is challenge. People are building. Say, take an example. This tomorrow SETS team are going to come. So SETS and IIT Madras, between these two institutes, there is a dedicated channel. See, is it that suppose we are using internet and we are able to use that open channel, we are able to have a VPN or whatever it is. Okay, but it's a dedicated channel, right? So that's the reason why QKD requires so many other years to get maturity and all that. Okay.
How do you know what data? Obviously, the redundant data. I have a confusion. So the block sphere, it seems that 1 kT is just 180-degree opposite to the 0 kT. But does it mean that A times 1 kT is equal to minus A times 0 kT?
No, please repeat.
I have some confusion.
Yeah. No, that part I understand. So you are here. Huh. Okay.
Can I write A times 0 kT?
Meaning, no, see, the point is this, sir. See, Now I am here. Okay. I need to move. I wanted to move. Classically, fundamentally, when any movement, is through, it's an operation. It should be an operator. The operator is what sir said is the gates. You apply Hadamard gate, from here you will move here. Okay, you apply X gate, you apply Y gate. There are phase shift gates, wherein which based on the phase, you will get rotation. Okay, so you can move from here to anywhere. See, we are not seeing here in 3 dimension. Why only here? I can move here, I can move here, I can move here, I can move here. What actually you are doing, you are shifting the phase angle. Okay, everything, the operator is through the operations or through the operators, through the gates. So this is I, this is minus say 180-degree phase shift. Okay. No, it is this. We have seen in a few slides back these points. The points. What is X point? I said this is X, this is plus. In a Cartesian product of X, Y, Z, this is 1, 0, 0. Right? That I have mentioned in a few slides back. Let us keep this point so that you will. Otherwise, it may take some time. Yeah. So you can this. Sir Arun sir, I think this got stuck. Huh? Okay, so this is the different measurement in different bases. This I will we have done this. This key distribution also in one way or other we already discussed. So the protocol what we discussed is called BB84 protocol. So wherein which you are having the quantum channel to communicate your your qubits and the classical channel to know about the basis, to understand the basis, whether the bases are common or not. Once the common basis is there, only corresponding bit would be used. Otherwise, you discard that this one, right? So you can see that in the classical channel, you are only sharing the basis, right? So this is the polarization angle I said, and yeah, so these are the bases, the linear basis and diagonal basis, and these are the polarization angles. And for angle 90-degree, you get 0 like this. Okay. Next, another interesting, which again we don't have in the classical, is the phase kickback. Yeah, again, see, it is all about that basis. So basis in which we have sent, basis in which the measurer could be the actual receiver, measurer could be the eavesdropper. Correct. So if suppose that's what, if if we are not worried about whether he would be succeed, we will not we hear about this is this, whether we are able to know that there is an eavesdropping. That point. That point. Yes. Yes. Yes.
That's why you think but authentic what we said about both things. That is the drawback of the more we is sent because there will be an error and people can detect the same from not correct.
And also error.
Error is also.
Okay, so phase kickback. Phase kickback is another interesting phenomenon in quantum computing algorithms, wherein which Morningstar was talking about 2-qubit states. In that, he said, if you remember, 2-qubit gates, the 2 qubits, one is called C, another one is called T. What is C and what is T? Control and target. So what happens actually? Control will say what would be the target. Okay. What happens in phase kickback is that you have a unitary U, and any phase that you would apply to the target state appears instead on the where it appears. Where it should appear on the target, rather it should appear on the control qubit. This is called phase kickback. Okay, so phase kickback is a phenomenon wherein which in a controlled application of unitary U, what is this unitary U? Is the operator. Any phase that you would apply to the target eigenstate appears instead on the control qubit amplitudes. You are supposed to get reflected on the target amplitudes, rather it reflects on the control qubit amplitudes. But how this happens? I think that so let me give you how this happens, because this phenomenon will not be there in the classical. So generally control says and target gets reflected, but here you are having a phase kickback. I will take this simple example. So we said the phase kickback means you have a control qubit and the target qubit. Generally, as per the control bit, your target bit will flips, things happens. Now, what is phase kickback? It's an interesting phenomenon in quantum computers, where as it says, when you apply the operator, the target eigenstate, instead of getting affected, you are going to get it reflected on the control state or control qubit. Let us see how it happens. Imagine I am having two qubits. Okay. The first one is the plus, which is the positive, that x state or that x basis plus, and another one is ket 1, right? So in that, my control one is plus and the target is the second one, right? The ket 1 is the target bit. So what is plus? It is the superposition 1 by root 2 ket 0 plus ket 1. Okay, this is my control and this is my target, right? So what I am doing is I am taking it as that, the tensor product, or 1 by root 2 ket 0 1 plus ket 1, right? Now this is my input. To the operator. What is the operator? CZ gate. So now when I apply CZ gate, we know 0 0 0 1 1 0 1 1, right? So when I apply CZ gate on 0 1, I am applying CZ gate on 1 1. So when I apply CZ gate on 0 1, what morning sir has said about this? What happens 0 1 on CZ gate? Because your control is, so 0 1 0 1. Now what happens with CZ over 1 1? CZ over 1 1. CZ gate, what happens? The target gets flipped, right? So the phase of the target gets flipped. So 1 1 becomes minus 1 1. That is the CZ gate. The morning sir gave the truth table. 2 qubit system. 0 0 means ket 0 ket 0 ket 0 ket 1. When I say ket 0 ket 0, it is control and target. So the reflection of it, what happens? So control and target, apply CZ, you get the control as it is and the target as it is, because control is 0. Now, but this phase gets flipped. That's why you are having minus 1 1. So same thing, for the convenience sake, what we have done is, I have written it as 1 by root 2 ket 0 minus 1 tensor product of 1. Convenience sake, we have written as a factorized form. So now what happens? This is my C, this is my T. My T is same. T got flipped. The phase got flipped. Plus became minus. So what is this plus and minus? Your phase got changed. That's called as phase kickback. Okay, this is called phase kickback. One of the interesting aspect in the quantum computing, where instead of target is being influenced, instead of amplitude of the target is being influenced, now what happens? Amplitude of the control is being influenced, and then phase of the control qubit got changed, and hence your plus became minus. Okay, this is called phase kickback. This I didn't get you. Control Z. So, see, I have directly written plus. I have directly written plus. If I take 0, apply Hadamard to get plus. A control is in the superposition. Ideally, even actually I have an example. I will leave it for you to solve it. Even if it is not superposition, phase kickback can happen. I have that example, but I'm not talking about that. But what is the ideal scenario is control to be in the superposition. It is easy to tell. Even if control is not in the superposition, you can have phase kickback. That example I'm not deriving it here. Another is an example. In the applications, okay, in the applications where actually, especially when you are developing the algorithms, where if you require, okay, it is like this, sir. Now recently, DST has called under the NQM what? Call for algorithms. Meaning what? Look, the theory is developed, there are no algorithms. Okay? There are no algorithms. See, in classical, you have, madam was asking about association, clustering, algorithms are there. Okay? You don't have algorithms. For that, we don't know of the problems, right? Which we have to apply. Everybody is telling that, see, for human genome analysis, apply quantum computer. Look. So it's very abstract, right? So point is phase kickback when you are building the quantum algorithms. So phase kickback, phase estimation, right? Then the no, see, the operation says, the kickback operation says, see, ideally what actually CZ is, now if you look at here, what actually CZ did, okay, so it has actually, you have, the, control and target, nothing, so control and target, your phase got this one. By taking this example, I am showing that this kickback can happen over the control one, not only on the target one. Okay. So wherever your application that demands the phase kickback, then the morning, a few minutes back I talked about the the phase estimation, or then especially the Simon's problem, where we are talking about period finding. Okay, so there, when the algorithms are built, this would be used. Okay, so this is one aspect of this one. So we have any questions? I think I have one more algorithm aspect, which is walks, that maybe we will discuss on the another day, where we have because I need to talk discrete and then quantum, then I can. So any questions? So QKD, as we were discussing, the QKD aspect is all about, if you observe, how we are going to utilize quantum computing for key distribution purpose. Okay. Earlier we said, because of quantum computers, security is in threat. Okay, all our security algorithms are in soup. So that is correct. But the positive side or the benefit of quantum computing towards security is, the best example is the QKD, key distribution. Okay. Please. So correct. So many of these companies like IBM, Google, they all have claimed that they have realized the qubits to some in number, 2 digit, somebody saying 3 digits, close to 1,000 kind of a thing. Okay. And some companies are bringing the chips with qubits in single digit in number. Okay. So a chipset having qubits, a single digit in number, 6 qubits, 5 qubits, kind of a thing. Correct. They could. Now, in fact, I was told that one of our alumni, he has a startup where actually they have built at the chip level, so yeah.
You probably they agree with the same they have thought that part of the computing is 20,000 times possible. Years. What are they? As Sarah saying, it's sort of what are they? Maybe the doing even maybe millions times more. But the process that we're on getting for part of the practice. I think one of the section of they go to the market. They are not an expert on that.
Yes.
But they are anything also. Quantum hardware device. Yeah, I can this on yes, it's because of that,
Maybe you give the mic to him.
So in paper pairs, actually, you have conducting qubits. So you have kind of junction, very weak link junction. So you send the current bifurcate in two directions. So they will come at the different links, and you measure the phase between them. What is the phase difference? And that phase difference can be used as a 1 qubit. Yeah. So depending upon how many Cooper pairs you can generate and how many you can control in that environment, that you can. He is working on photonic based actually. Yeah. So photonic based, you have polarization. So you take the one source and you just put through the waveguides channels, so to get them entangled, so that, and just check what is the correlation between them, both the photons coming. So if you know what is the G correlation of that, then you can say that what is the entanglement between those two. Yeah.
Oh, that's what. Yeah. So if you see, the term itself is phase. When you are moving from plus to minus, what do you mean by that? You are rotating by 180 degrees. Okay. That that change from plus to minus, meaning you are in the same base, but we are talking about the phase. So you are changing from plus to minus with an angle of 180 degrees. Okay, so the phase change. So the phase kickback that has happened. Okay, so that is the phase. That phase, that angle is the estimate. For that, there is an algorithm, quantum phase estimation algorithm. But what we are talking here is only phase, not about the base. No, no, no. Can you repeat the question? No, no, it is this. It is this. I think, you look at this, the block sphere. Actually, it is this. I am here, madam. I can, from here, I can go to any point. From here, actually, for illustration purpose, we are seeing with the basis for reference points. You anywhere to anywhere. Yes, that is why we are saying infinite. So in this, just if you look at this, just this illustration only, if you look at this diagram, again, we are talking only with the single qubit. As morning Sarah also was talking, it's about single qubit, right? Now you see, you can be any, just that is the point is, the moment you are here, this forms the basis. For the understanding purpose, we took three bases. What are that? Z, X, Y. We can define our own basis. Correct. Correct. Yes. Reference basis. It is the other way. You can take point that for that, there will be certainly in one basis. Understand? Correct.
Here.